This is everything you need to know about elimination reactions. Let's say the question says, for the following reaction, show the mechanism and determine if it is SN1, SN2, E1, or E2. Step 1. On both reagents, draw in all lone pairs on every atom that needs them and draw in all partial charges. So what atoms want electrons, hence are electronegative, withdrawing, delta minus, and what atoms are delta plus because they're beside a delta minus atom, hence their electrons are being taken from them, delta positive. Where your delta minus things are potential nucleophiles because nucleophile is nucleus loving, hence minus charge. Your electrophiles are going to be the possible delta plus things, hence the things getting attacked by the nucleophile. For this question, it's not as straightforward as conventional examples, so what we need to do is we need to try to find the most acidic proton. As we see, there's a lot of hydrogens here. So which one is the most acidic, hence the most likely to leave? What we do is we evaluate the stability of the conjugate bases. If you draw out H2SO4, you see both of the hydrogens attached to the oxygens for delta plus because they're beside delta minus oxygens. The conjugate base means you lose one of the protons. What happens? Okay, we get an O minus. Is this stable? Yes, it's stable via resonance and inductive effects. Now let's look at the conjugate base for the hydrogen on structure number 1. The resulting conjugate base has a minus charge on an oxygen. Okay, that's fine. What is it attached to? Well, there's no resonance and it's attached to a 3' carbon. That means there are groups that can donate to that carbon center, hence it's an electron-rich carbon center. Electrons hate each other. This O minus is beside something that wants to give electrons to it. Repulsion. Unstable. So the conjugate base of H2SO4 is much more stable than the conjugate base of structure number 1. Hence, that is the most acidic proton on H2SO4. That is the delta plus center. It's the electrophilic center. So step 1, now we draw our head of the arrow pointed at the most delta plus thing. Hence that hydrogen that comes from the structure with the most stable conjugate base. Step 2, you draw the back of the arrow from the most electron-rich atom on the other structure. This is going to be your nucleophile, hence our oxygen, delta minus, back of the arrow. Step 3, connect those arrows, 2 in, 2 out. That's your reaction. The 2 in arrow always results in a new bond, so that lone pair on the oxygen becomes a bond to the pink hydrogen. And now that oxygen has a positive charge. Oh wait, this is a leaving group. This is almost water. So what happens if this OH2 group with a positive charge took 2 electrons and just left with them? You get a resulting 3' sp2 trigonal planar carbon center. This is stable because it has alkyl groups that are electron donating attached, hence it gives electrons to the positive charge, stabilizes it. We also have a resonance stabilization because the pi electrons in benzene can go 2 in and also stabilize that positive charge. Hence, this is most likely going to be a 1-type reaction, a stable reaction. Now, how do we decide if this is substitution or elimination? Well, there's heat involved. Hence, this is most likely the removal of water. So water's already left. So we do not want to reintroduce water into the structure. So, well, what else can water do? Well, water's a base. There's lone pairs on that oxygen. Hence, it can go and attack a hydrogen on a beta carbon. Just a reminder that beta carbons are the carbons that are 1 carbon away from the carbon with the positive charge. And you go and you attack the hydrogens attached to those carbons. To attack the hydrogen that results in the most substituted double bond. Hence, you want to attack the hydrogen on the carbon group that's further away from the benzene ring, because the resulting double bond is 3' substituted. Hear me out. Let's look if we attack the other beta hydrogen on the top carbon. What do we get? The resulting double bond via 2 in, 2 over electron movement is only 2'. 3' is more stable than 2'. Hence, it's going to be the first reaction. But now, the first reaction could either be E or Z. Which one do we want? Which one's more stable, more favorable? Well, the less sterically hindered one, hence the E, where the 2 larger groups where you evaluate atom by atom on each side of the double bond are further away from one another, hence on opposite sides of the double bond. That's it, that's all. Hopefully this helps.